Good.
Physical science time. Let's call this one machines, efficiency, and mechanical advantage. We're going to do this in not that order.
Where's the...
Machines, efficiency, and mechanical advantage. Basically, section 2 of your book is about what machines are good for, and then section 3 is about what kind of simple machines and complex machines there are. But basically, let's remind ourselves of something here first. This is called, let's remind ourselves of the law of conservation of energy. What does that mean? What's the law of conservation of energy?
It's the law to where the universe has its amount of energy that cannot change.
Yeah. So basically, energy can be what?
Can't create it or destroyed.
Yeah, but it can be transferred. It can be transferred, and changed is fine, but it can be transferred. Oops, I should put a comma. Or transformed, but not created or destroyed. So basically, what this means is that energy in must equal energy out. For any system, however much energy we put into the system has to come out of it. It has to be the exact same. What do we measure energy in? Joules. And what do we measure energy in? Joules. What this means for simple machines is that that's also true of the work. Work in must equal work out. What's a good way we can remember that? We know this from the law of conservation of energy. How can we remember that that's true of work too? Well, they're both measured in joules. So basically the amount of, I don't like it when people say units as a type of measurement. Like sometimes someone will say, how many feet tall are you? I don't like that. I like it, what height are you would be a better thing for me. But you can remember it as the joules, the amount of joules that go into a system must be the amount of joules that come out. Whether it's energy or work doesn't matter. Because of the law of conservation of energy. This is a truth of the universe. This is one of the things that makes the universe work. This is one of the things that we understand about the universe that makes it the way it is. So effectively, when we're using a machine, can it increase the amount of energy that we put in?
Yeah.
No, it can't change. The amount of energy can't change. Even if, and we're not mostly talking about these, but even if we're using an electric or a gas-powered machine, like a chainsaw or an impact driver, is more energy going into the system than what we put in? No, because we're also using some other external power source. An internal combustion engine in the case of the chainsaw, or a battery which was charged from an electrical outlet in the case of the impact driver, or whatever. But we cannot ever have more energy being used by a machine than what we put in. What do you think?
So like, say I'm in a skid steer and I want to go forward, so I press my sticks forward. So the energy that I just put in causes the skid steer to move
What
forward.
you're really doing there is you're opening a throttle, so the tiny amount of actual physical energy that you yourself put into the levers to move them, all that did was open a throttle, which allowed more gasoline or diesel to get into the engine matrix, which then made the engine go faster, which then made you go forward.
Yeah.
So you're not really pushing it in that case. We're going to be focusing primarily on things where it's actually like hand machines. That's why we're calling this, I should have put up here, simple machines. And by that I mean unpowered, relatively uncomplicated, because they're easier to understand. All this is true for powered machines too, except in those cases, some of the energy in is also supplied by electricity or internal combustion or some other kind of energy source.
I push my lawnmower.
It's more like if you push an old-timey lawnmower that doesn't have any power of its own. And the energy you're providing spins the thing, and you push it along with it. So anyway, what this means is that what simple machines can do, let's just do that. Let's get the types of simple machines out of the way real quick, just so that we can be clear on this. We talked about these last year, so they should be a review. What are some types of simple machines? Simple machines. That's not one of them. Lever is one of them. And we're talking about broadly speaking. Maybe old-timey lawnmower is made of several different kinds of machines, but it's not one of the basic types. Lever is one. Pulley. What's another one?
The inclined plane.
Inclined plane. What's another one?
Button.
Button isn't one of them. Now you're thinking of Minecraft things now.
Wheel and axle.
Wheel and axle. wheel and axle,
Screw.
screw, and then there's one more,
Wedge.
wedge.
He's looked through his book.
That's okay. That's okay. I'm gonna just switch these two real quick. They're all the same, so if you wrote them down, that's fine. I'm just gonna switch these two so that I can show you something. Wheel and axle, and then this one is inclined plane. And the reason I did that is because these three, let's say, these three on top that I put are all kinds of lever, and these three on the bottom are all kinds of inclined plane. And there are videos on my channel that you can, or there are real videos on YouTube by people who know what they're talking about and who are good and probably good looking. But there are videos out there that will explain to you exactly what these are, and some of them are on my channel, but we're not going to really focus on this. These are the types, and all of these have a certain what we call mechanical advantage and an efficiency, and they have to do with this. This is what we're going to talk about today. So all of these, can any of these change the amount of work that's done? No. So work, and I like to do this, I like to show that these things are equal by making them the same size. But remember that work is made of two quantities. What does work multiply? I mean, what does work depend on? What two quantities does work depend on? Force and distance. So what they can do, work in must be equal to work out. But they can make the force smaller to make it go over a larger distance.
So let's think screw one of the simple machines.
Yeah, it's already up there.
Oh, okay.
So they can change the distance, right? You can apply a larger force to make it go a smaller force but a larger distance, like in the case of the inclined plane. They can do the reverse of that and make it go a larger, smaller distance but apply more force, like in the case of most levers. You see what I'm getting at? The work has to be the same. The work that you do must equal the work that the machine outputs, always. But it can change the amount of force. For instance, a car jack is not really a simple machine, but it's a combination of several ones. You can't lift a car. You can't just go whoop. So if you need to change the tire, you can't do that. But what you can do is you can put a small force over a large distance to make the car go up just a little. A small distance, but a large force. It'll actually lift the car. And you do that several times, and eventually the car gets lifted up. You can also do the reverse, where we use, this makes our force smaller, but over a large distance. Like if we're pushing a box up an inclined plane. What was your question?
That was kind of what our lab was about.
Yeah.
Like, the more time it takes over a longer distance means you're not putting in as much work.
You're not using as much power in that case.
Yeah, that's right.
Yeah, when there was more time spent, less power was used, but it's the same amount of work both ways. Yes.
Can you read the equation out to me because I can't see it?
Just scooch over here so you can see it. And then this idea of mechanical advantage talks about how mechanical advantage, which we just label MA usually, equals force in divided by force out.
What's that top word?
I'm sorry, that's reversed. Force out divided by force in. I thought I was wrong, and I was. Force out divided by force in. Mechanical advantage. So what this tells us is how much the machine is helping us. How much it reduces the amount of force that we need to do. There are different calculations. Several different machines have different ways of calculating mechanical advantage, or what we call ideal mechanical advantage. For instance, a lever, the ideal mechanical advantage, how much mechanical advantage could possibly be gotten out of it, is the length of the input arm divided by the length of the output arm. And so if I use this as a lever, basically, this is just an example because we're running out of time, but if I use this as an example, I wonder if the camera can see that. Is this picking up on the camera, Justice?
Yeah.
Okay. So if I use this as my lever, you can see, just by looking at it, that I would be able to lift a heavier object. This is not a heavy object, but I'd be able to lift a heavier object here. That's why we use levers a lot of times. If there's a really stuck door, we might use that kind of lever to do that. And the reason that works is because we're dividing the input arm here by the output arm. So that makes a great big number.
Are you teaching us how to use a crowbar?
Yeah. Breaking into someone's house tonight, that's your homework. No.
Yeah!